Chapter 6 is on positive definite matrices. In this chapter, we are specifically going to look at the singular value decomposition. So, chapter 6 is on positive definite matrices. Positive definite matrices. And our focus in this chapter is only going to be on singular value decomposition, which is the counterpart of eigenvalue decomposition, which is specifically for square matrices, while you can extend the singular value decomposition to rectangular matrices too. So before we do this singular value decomposition, let me define some terms or some forms. So the first is the quadratic form. So quadratic form in the linear combination is a linear combination of xi, xj, where ij may be equal, or we say q of x, this is the vector x, q of x is x transpose ax, which is x dot x, the dot product with ax, and this we assume A transpose equals A. So if x equals C1 V1, linear combination of eigenvectors, C2 V2 plus Cn Vn, where Vi 1 to n are orthonormal eigenvectors, eigenvectors of A, then this implies A times x. So I multiply A over here. If I multiply A here, I multiply A here, I multiply A over here. So I'll get C1 A times V1 plus C2 A times V2 plus so on plus Cn A times Vn. But A times V1 is lambda 1 V1. This is lambda 2 V2. This is lambda n Vn. So we have A of x equals to C1 lambda 1 V1 plus C2 lambda 2 V2 plus so on plus Cn lambda n Vn. Okay. And what is q of x, or q of x is simply x transpose. So x transpose is, maybe I use this parenthesis here, C1 V1 plus Cn Vn transpose, and A times x is C1 lambda 1 V1 lambda 1 V1 plus Cn lambda n Vn, or this is equal to, when I take the transpose and I multiply, this is simply C1 square lambda 1 V1 transpose into V1 is V1 this norm square plus C2 lambda 2 V2 norm square. The cross products are 0. Why? Because these are orthonormal eigenvectors, and since these are orthonormal eigenvectors, these norms are 1 plus Cn lambda n Vn square. So orthonormal implies v dot vi dot vj, this is equal to 1 for I equals j and 0 else. So that's why the length is 1, the norm square is 1, otherwise it's 0. So this is equal to c1 square lambda 1 plus c2, sorry, it's not, yeah, c2 square, this is also c2 square plus cn square plus c2 square lambda 2 plus cn lambda cn square lambda n. Okay. What is an equivalence transformation? What is an equivalence transformation? We have looked at the similarity transformation. What is an equivalence transformation? So equivalence transformation. So one of the equivalence transformation is the congruence transformation. Congruence transformation. And what happens in the congruence transformation? In the congruence transformation, A hat equals Q Hermitian AQ, where Q is non-singular. Q is non-singular. This is called the congruence transformation of A. Congruence transformation of A, or this implies A and A hat are congruent. A and A hat are congruent. So congruence transformations a congruence transformation arises naturally with quadratic forms, in which A is symmetric or Hermitian. Then this implies A hat is also symmetric or Hermitian. So if I take the Hermitian of this relationship, if I take the Hermitian of both sides, this will be QH, AH, but since it's Hermitian matrix, A is Hermitian, so AH is equal to A, and this is Q. So we still have A hat H is equal to A. So if Q is unitary, then congruence transformation is same as the similarity transformation. Then if Q is unitary, then congruence transformation is same as similarity transformation. Let's define some terms. What is inertia of a matrix? Inertia of a matrix is I, J, K. What is I? The number of positive eigenvalues. J is the number of negative eigenvalues. And K is the number of zero eigenvalues. Okay. So inertia of A This is inertia. So inertia of A is equal to the inertia of QH for a non-singular Q. Besides the inertia, there's another thing, which is the signature. So signature is written as SIG. So signature of A, or signature of A, is I minus J, the difference between the positive and negative eigenvalues. So this is the difference between positive and negative eigenvalues, between the number of positive and negative eigenvalues. And then you have the rank of A. This is the rank. And what is the rank? Rank is simply I plus J, and this is the sum of the positive, sum of the nons. This is the number of non-zero eigenvalues, number of non-zero eigenvalues, and these two, we have right rank here. These two are preserved under a congruence transformation. Preserved under a congruence transformation. So the difference between the positive and negative eigenvalues and the sum or the rank or the sum of the number of the number of non-zero eigenvalues is preserved under a congruence transformation. So this is all I want to talk about, some definitions, and let's move on to the main topic of this chapter, which is singular value decomposition. And in my first lecture in this course, I actually told you what is the why is singular value decomposition so important from a practical point of view. So singular value decomposition, A, which is an m by n matrix, can be written as U, which is an m by m unitary matrix, sigma, which is an m by n diagonal matrix, and V, which is an n by n unitary matrix. So this will have left singular vectors of A, left singular vectors of A, and we'll define what is the singular vectors of A, and both U and V are unitary matrices, not necessary transpose of each other, not necessary transpose of each other, where U and V are unitary, and sigma is a diagonal matrix, is a rectangular diagonal matrix. Okay, so SVD is closely associated with eigenvector factorization, with eigenvector factorization, which is Q lambda Q transpose of a positive definite matrix, What is a positive definite matrix? Where this Q has orthonormal eigenvectors. Just to recall, this has orthonormal eigenvectors. vectors. Okay, so what is the positive definite matrix? So here's the definition. For a real symmetric matrix to be positive definite, for a real symmetric matrix to be, and this is by the way sometimes written as PD, is to be positive definite. So there are some of these definitions. First one is X transpose A times X is strictly positive for all X not equal to 0. Okay. All the eigenvalues are positive. All upper left submatrices. So upper left submatrices are these. So this one, and this one. So all upper left submatrices have positive determinants. By the way, this also implies the determinant of A is positive. Why? Because the product of the eigenvalues is the determinant of A. So all upper left submatrices have positive determinants, and obviously, by the way, the largest left submatrix is the matrix itself, have positive determinants, and all pivots without row exchange satisfy dk greater than 0. So all pivots are also positive. Okay, so why do we need singular value decomposition? The simplest reason is eigenvalues for a rectangular matrix are undefined. For a rectangular matrix are undefined for the simple reason you cannot compute the determinant of A minus lambda I where A is not a square, are undefined. And the diagonal but rectangular matrix, and I'll tell you why it's diagonal but rectangular matrix sigma has eigenvalues from A transpose A and not A. By the way, the non-zero eigenvalues, you can check the non-zero eigenvalues of A transpose A and A transpose are equal, maybe, are same, is also quite fine. Okay, so positive entries which are in positive entries in sigma 1, sigma 2, sigma r. Why? Because R is the rank. It's the rank of A, and since it's the rank of A, this will tell you how many non-zero eigenvalues are there. So are the singular values. Positive entries, these are the singular values of A. So first you fill. So what we'll do is we will fill first R spaces. r spaces on main diagonal when rank of A is R and others are zeros, Okay. For any A, H, A is Hermitian and positive semi-definite. Also, for a positive definite matrix, you'll always have an inverse. Hermitian and positive semi-definite. So what is positive semi-definite? Zero is included. Hermitian and positive semi-definite. This implies the eigenvalues are greater equal to zero. So there is an equal to zero here too, where sigma of A, the singular values, where are the singular values? So singular values of A, these are the singular values of A, are simply the square root of the eigenvalues of A, H, A. So these are the eigenvalues, the non-zero eigenvalues of A transpose A Hermitian A. Okay. So rank of A, H, A is same as the rank of A, which is the number of positive. So the singular values are either positive or zeros. Number of positive sigma I, because it's the positive square root over here. And if A equals AH, so if A is A Hermitian, this implies sigma A equals lambda of A, the absolute value of the eigenvalues of A. So any m by n matrix, any m by n matrix can be factored into A m by n equals u m by m sigma m by n and v transpose n by n. So these are orthonormal matrices. So ortho, or if it's complex, then this would be unitary. Orthonormal, or maybe I say unitary. Orthonormal or unitary matrix. Same here, orthonormal or unitary matrix, and the columns are eigenvectors of A transpose. Here the columns are eigenvectors of A transpose A. This doesn't mean we have to find separately the eigenvectors of A transpose A and the eigenvectors of A transpose, because then this will be an enormous problem to solve, which we don't want to do that. And I'll tell you what is the simplest thing here, and where this sigma m by n equals like this. This is a diagonal matrix of R. Since this is m by n, this is R. Obviously, this is R because this is a diagonal matrix. This is m, so this has to be m minus R. So when we add up the number of rows is m minus R plus R, which is R. So since the number of columns is n, so this should be n minus R. Obviously, this is R because this is R. This is a partition matrix, and this should be also m minus R. This is 0. This is 0. Depending on the values of m and n, these can be scalars, these can be vectors, or these can be matrices. Okay, where where maybe not, shouldn't have where twice, where sigma r is simply sigma 1, sigma 2, and sigma r. This is a diagonal matrix. And just like we did for the eigenvalue case, we'll say sigma 1 is greater than sigma 2 greater equal to sigma r, which is greater than 0. If all non-zero singular values are here, everything else is a 0, right? So these ones, these ones are simply the square root, square root of the eigenvalues of A transpose A or AA transpose. So non-zero, the non-zero one. So these the singular values. So these are non-zero, square root eigenvalues, eigenvalues of AHA, or maybe I want to do AAH. So these are non-zero. So non-zero eigenvalues of AHA or AAH or AAH are on main diagonal. Are on main diagonal. Okay. And for positive definite matrices, where there is no zero, so this is the difference between positive and positive semi-definite. So positive semi-definite has eigenvalues, can have eigenvalues that can be zero, which means invertibility, inverse is not possible. So for positive definite matrices, sigma equals lambda, and U sigma V transpose is identical to Q lambda Q transpose. For other symmetric matrices, any negative values, obviously we can have negative definite and negative semi-definite matrices too. Any negative values in lambda become positive in sigma. Okay. And for complex matrices, as I said before, for complex matrices, sigma remains real. However, UV become unitary. Which implies, in general, the S3 decomposition like this: A is equal to U sigma V Hermitian. Okay. And let's see how do we calculate these singular values, singular vectors. And so let's write A again. So A is U sigma V transpose. Let me write the dimensions to m by n. These are square matrices, so obviously they are square. M by n and n by. These are orthonormal matrices, so obviously they have to be square. And this I can write as A, or what I can do is I can multiply V on both sides. I can multiply a V here, and I can multiply a V. I can multiply a V here, and I can multiply a V here. If I do that, I have, so this implies A times V equals U times sigma. So if I write this one, this will be A V1, A V2, AVN, AVN, and this will be equal to, this has R non-zero value. So the sigma has R non-zero value. So this will become U1 sigma 1, U2 sigma 2 up to UR sigma R, and then it will be 0, right? It will be 0, and this is the matrix I have. Yeah, why is this like? Because R non-zero sigma I are on main diagonal, or on main diagonal of the rectangular matrix sigma, right? Okay. And then before, yeah, that's fine. And then this implies, so this implies this vector equals, this column vector equals this one, and up to R of these. So AVI equals sigma I UI for I is equal to 1 to R, right? And AVI equals 0. So somewhere here, after we have some R, then we have this one equal to this one over here. So this is equal to 0 for I equals R plus 1 up to, since these are n, so I is equal to R plus 1 to n. So this implies what? So this implies, so this one implies null space of A spans VR plus 1, VR plus 2 up to Vn, and this implies, so what is this? This is simply AVI gives you the column space of A. So UI is in the column space of A. So this is B vector, if you recall from chapter 1, chapter 2. So AVI is the combination of column space. So column space of A spans what? This spans these vectors. So column space of A is actually a combination of columns of U. So column space of A spans U1 up to UR. And when do we use these equations? So we are going to use these equations when, use them when A is fat. A is fat meaning implies M is less than n. Okay. So if A is fat when M is less than n, this implies A transpose is M by M. It's M by M. So when it's M by M, I can easily find. So from A transpose, which is M by N, find eigenvalues and corresponding eigenvectors. And what are those eigenvectors? These are the eigenvectors which go into matrix U, which are columns of, eigenvectors which are columns of U. Okay, so columns of U. So once we once we find them, I'm sorry, this is not for a fat matrix. This is for a tall matrix. When A is tall, I'm sorry. When A, because I want to find V's actually. So When A is tall, this implies n is n is less than m. So A transpose A. So A transpose A is n by n. A transpose A is n by n. When it's n by n, we can find eigenvalues corresponding, find eigenvalues of A transpose A and the corresponding eigenvalues, and these are the columns of V. These are the columns of V. Why this one? Because if it's tall, this will be of a smaller dimension than AA transpose. Because AA transpose is going to be of m by n, m by m, and obviously since n is smaller, so obviously this is a smaller matrix and I can easily calculate the eigenvectors of it. So whenever you have a tall matrix like this, whenever A is like this, so if this is A, use this equation. Okay. And what is the other equation? So the other equation is also A is equal to U sigma V transpose. So this implies A transpose equals V sigma transpose into U transpose, right? Or if I multiply U on this side, if I multiply U on this side, I multiply U on this side. So this implies A transpose U equals V times sigma transpose, right? So this one, A times U, is going to give me A transpose U1, A transpose UM, right? Because these are m of these, and this is equal to sigma. When I do sigma transpose, I still have R non-zero values. So I have sigma 1 V1 goes up to sigma R VR. Then I have again 0, and I have 0 vectors over here. So again, this first one is going to be equal to this one, and so on correspondingly. So we have, or this implies, or A transpose UI equals sigma I VI, and this is for I equals 1 to R, because these are the R non-zero values. And for all others, A transpose UI, this is equal to 0 for I is equal to R plus 1, goes up to M. Okay, so this implies, so this is again, this implies UI belongs to where? UI belongs to the null space. So this implies null space of A transpose spans, null space of A transpose spans UR plus 1 up to UM, and this one implies, again the column, so this is the row space now. So this is the row space spans V1. So column space of A transpose spans V1 up to VR, right? And when do we use these equations? So when do we use these equations? So we use these when A is fat. A is fat meaning A is like this, implies A is like this. So if A is fat like this, this means M is less than N. If M is less than N, then this implies A transpose is M by M. And obviously this has smaller dimension than A transpose A, which is N by N, because here N is greater than M. And we find eigenvalues. So find eigenvalues and corresponding eigenvectors, corresponding eigenvectors, which are the columns of U, So once we have U, I can compute from here the RVIs, and for the other VIs, I can actually go here and find the rest of the vi's I can find from the null space of A. And similarly, I can find the remaining ui's. So either I find ui's from here, so A, V, I, ui's, and the remaining ui's I find from the null space definition over here. Okay. So just to check here, V contains, and same is the case for U, V contains orthonormal eigenvectors of A, H, A. And how do we prove that? So A times Vi dot A times Vj. This is equal to A times Vi permission into A times Vj, which is equal to Vi permission AH A into Vj. What is AH A Vj? So AH A Vj is simply actually this should be sigma square. It should be sigma square j. It should be sigma square j Vj, right? It should be sigma square j. So this should be some sigma square j. So actually this one. So this whole thing should be sigma square j Vj, because these are the singular values which are the eigenvalues of this matrix. So we have, so this is equal to sigma square j into Vi h into Vj, which is equal to 0 for I not equal to j, and equal to sigma square j for I equals to j, because Vi's are orthonormal matrices. Okay. Okay. And before we go on, so recall when we wrote A equals Q lambda Q transpose, when we wrote A equals Q lambda Q transpose, where Q's are orthonormal eigenvectors, orthonormal eigenvectors of A in chapter 5. So we said we had that spectral decomposition. So we had the spectral decomposition, and that spectral decomposition was A equals summation L lambda I E transpose I is equal to 1 to n, which is simply equal to lambda 1 E1 transpose plus lambda 2 E2 transpose plus lambda n En transpose. All these are rank 1 matrices. Right? All these are rank 1 matrices. We can do the same thing here. So similarly, when A is equal to U sigma V transpose, this implies A equals, instead of lambda 1, we'll have sigma 1, you'll have U1, you'll have V1 transpose plus sigma 2, U2, V2 transpose plus obviously up to R, VR transpose, VR transpose. So this tells you, just like this expression told you, you can always threshold and get rid of some of the sigmas, which simply means you can actually reduce the dimension of your feature space if we are talking about the in the machine learning context. Okay, so eigenvectors of AA transpose and A transpose A must go into columns of U and V. And how do we prove that? So A transpose, this is M by N into N by M. So this is an M by M matrix. This is equal to U sigma V transpose into U sigma V transpose whole transpose. So this is equal to U sigma V transpose. We reverse the order here. So this is V sigma transpose into U transpose. This, by the way, is identity because this is an orthogonal matrix. So this is U sigma sigma transpose sigma transpose into U transpose. So obviously these two matrices are similar because they have the same eigenvalues. So columns of U are actually the eigenvectors of Ka transpose. Similarity transformation. So this one and this one are similar. So obviously these are the eigenvalues of the similar values of the similar, and these are the columns of our U's are contains eigenvectors, and since it's orthonormal eigenvectors, contains eigenvectors of A transpose. And remember, this is a symmetric matrix, so we will always have a full set. So there's no need to worry about the Jordan form. So this is a symmetric matrix, so we'll always have a full set of eigenvalues. Also, A transpose A is U sigma V transpose whole transpose into U sigma V transpose. This is equal to, again, you reverse order here, so it's V sigma transpose U transpose U sigma V transpose. Again, this one is identity, so we are left with V sigma transpose sigma into V transpose. Again, these contains, so again these are similar, and contains eigenvectors of A transpose A. And again, this is also a symmetric matrix, so we have a full set, so no need to worry about the Jordan form again. Okay, and this one, by the way, is M by N. This is N by M, so this is an N by N matrix. So this is an N by N matrix, and this, by the way, is an M by M matrix, both symmetric. Also we can say from here, this also implies A transpose A times V of J is some sigma square J Vj. Right? This is the eigenvalue equation. So A transpose A, so this is the matrix with vector, and this is the scalar, the singular value or the eigenvalue of this one times the vector. Okay, or I can do is if I multiply A here, so A times A transpose A, or maybe I change the value here, or so if I multiply A over here, I multiply A over here, so I get A transpose A times Vj, right? So this is the new vector equal to sigma square J A times Vj, right? So this is the eigenvector. This is the eigenvector of A transpose. So this is the eigenvector of A transpose. And what is the length of this vector? So the length of this vector. So what is the length of AVJ? So the length squared of AVJ is AVJ Hermitian into AVJ, which is equal to VJ Hermitian A or A transpose times VJ. But A Hermitian AVJ, this is simply this one, sigma square JVJ. So this is sigma square J VHJ into Vj. This, by the way, is simply Vj norm square, and this is equal to 1. If this is equal to 1, so this thing is simply sigma square j, or the length of E, so this implies length of, or maybe I just write this thing. So length of AVJ is simply sigma j, right? If the length of this one is sigma j, if I divide both sides, so this implies AVJ over sigma j, this is simply uj. This is my unit vector. So since this one, so the eigenvectors of AA transpose are actually the columns of U, then there are the columns of U. So I can say, see, this AVJ is actually the unit normalized vector, which is a column of U. And from here I get A times V equals U times sigma. So when I multiply V transpose on both sides, I get my singular value decomposition, right? Or A equals U times sigma V transpose. If I multiply V transpose here and I multiply V transpose here. So this is a formal, semi-formal proof of the singular value decomposition. So let's do some examples. Let's do a couple of examples and then look at the application. So the first example is A has one column. A has one column implies R is equal to 1. This implies sigma has only sigma 1, right? Because A has one column mean R is equal to 1 or N is equal to 1. Maybe I write N is equal to 1. R is equal to 1 or N is equal to also 1. So A is like this. A is minus 1, 2, 2. Okay. So if A is minus 1, 2, 2, what is A transpose A? So A transpose A is minus 1 square plus 2 square plus 2 square, and this is 4, 4, 8 plus 1. So this is 9. This is 9, and this is the length. This is the length there, and this is equal to some U, with, so this is 3 by 1. So this is going to be 3 by 3. There's going to be a sigma. The sigma is 3 by 1. And then I'm going to have a V transpose, which is 1 by 1, so that I get a 3 by 1 matrix. So what is this sigma? This sigma is simply the square root of this one. So this sigma is 3 by 1. So this is a 3 square root of 9. So this is square root of 9, which is the singular value. And then I have 0 and I have 0. Right? Okay. And what is V? V is 1 by 1, so obviously this is non-zero, so this V is 1 here. Okay, because this has to be normalized. This has to be normalized to 1, so obviously this is 1. What about U? So U, since this is a tall matrix, so for the tall matrix, I think I told you to use A times Vi equals Ui for I is equal to 1 to R. So this is only one column, so one column independent, so obviously R's rank is 1. So R is equal to 1. So for a tall matrix, use this one. So if this is true, so or A times V1 equals U1, and this U1 is simply A times V1, means V1 is a scalar, so obviously we get back this matrix here. So we have minus 1, 2, 2. This is not normalized, so I say where the length of U1, the length or the norm of the length of U1 is 4 plus 4, 8 plus 1, 9. So this is under root 9. So this one is 9. So the length is 3. So I say 1 over 3. So now this matrix is normalized. So this is U1. So I need two other matrices, two other columns here. So for other values, I want A transpose Ui should be equal to 0. This should be equal to 0 for I equals R plus 1 up to M. r plus 1 up to m. M is 3, so this is 2, this is 3, right? This r, by the way, is 1, so only we have one vector. So we need to find A transpose. So what is A transpose? So this is minus 1, 2, 2, and then I have this vector ui equals 0 for I equals 2 and 3, right? And this I can write as this one. So x minus 2y minus 2z equals 0. So this implies x is equal to 2y plus 2z. So these are my free variables. I can put any values, but the problem is I have to get a vector which is orthogonal to this one. Otherwise, I have to apply Gram-Schmidt. So I can assume I can take these two values. If I take these two values, so these are my two vectors. So this is u2 and this is u3. Both need to satisfy this condition, this equation, or maybe this equation, and they also need to be orthogonal to each other. So obviously, for distinct, so they will always be orthogonal to these two will always be orthogonal, but you need to select these two so that these are also orthogonal. So I say if y, maybe I also put 1 over 3 here. I put a 1 over 3 here, and then I select 2 minus 1, 2. If I do that, so this is x, so x is 2, y is minus 1, z is 2. So is my equation satisfied? So let's see. So 2 plus 2, 4, minus 4 equals 0, so it's all right. And then here I select 2, 2, and minus 1. If I do that, so again my x is 2, my y is 2, and my z is minus 1. So let's say 2 minus 4 is minus 2 plus 2, again this is 0, and let's see, are they orthogonal? So 2 into 2 is 4, minus 2 is 2, minus 2 is 0. So both are orthogonal, and obviously they are orthogonal to this one. So this is minus 2 plus 4, which is plus 2, minus 2, which is 0. Again, the length of this one is 9. So the length of this one is 3. So I normalized by 3. Again, check this one and this one. So 2 into minus 1 is minus 2. Minus 2 minus 4 plus 4. So obviously these are orthogonal. So my u is like this. So my u is minus 1 over 3, minus 1 over 3, 2 over 3, 2 over 3, and here I have 2 over 3, minus 1 over 3, 2 over 3. Again, I have 2 over 3, 2 over 3, minus 1 over 3. So if I had applied my free variable and pivot variable approach, then I would have gotten vectors which were not orthogonal. So I would have to orthogonalize them. So if you can select in some way, so have some procedure to find. So this is an equation in which there are 3 unknowns and there is only one equation. So obviously you have many solutions. So you can pick vectors such that they are already orthogonal without applying the Gram-Schmidt procedure. Otherwise you have to do a Gram-Schmidt and then get it. So if you do, so check A equals U sigma V transpose, whether this is all right or not, whether this is equal to minus 1, 2, or 2. So check this one, whether this holds or not. Okay. Let's look at another example. So another example is, so we'll do both. We'll now do a fat matrix 1. So the fat matrix 1 is, so A is equal to, for example, minus 1, 0, 1, minus 1, 0, and 1. Okay. So this implies A transpose is minus 1, 1, 0, 0, minus 1, 1. Okay. So this is a fat matrix. So this is 2 by 3. This is 3 by 2. So it's easier if I do A transpose. if I do AA transpose, and from AA transpose I can get columns of U, some columns of U, some columns of U. So what is AA transpose? So AA transpose is going to be a 2 by 2 matrix, 2 by 2 matrix. So minus 1 plus 1, minus 1 to minus 1 is 1, 1 plus 1 is 2, 0, minus 1, minus 1, and obviously this is symmetric, so this is symmetric over here. So again 0, 1 plus 1, again 2 over here. So this implies AA transpose minus lambda I equals 2 minus lambda square, 2 minus lambda square, minus minus plus minus 1 equals 0. So this I can also write square here. So again I have a square minus b square. So a square minus b square is a minus b into a plus b. And this is equal to 0, this is equal to 0. So which one is the higher one? This one is the higher one. This is 1, this is 2. So this implies lambda 1 is equal to 3, and this implies lambda 2 is equal to 1. So again we can check. So 3 plus 1 is 4. So this is trace is 4. This determinant is 4 plus 4 minus 1, which is 3. This determinant is the product of this one, which is 3. Okay. So I'm not going to calculate A transpose A, but just for you, you can check A transpose A. I'm not going to use it, but just for you, you can check A transpose A is going to be, so we weight the first row by minus 1, so it's 1 minus 1 0, 1 minus 1 0. Second one is you subtract the second from the first, so this one is minus 1, this one is 2. Again, this is a symmetric matrix, so this has to be 0, and this one is minus 1. Obviously then this one is also minus 1. And finally the third one, you actually pick the third one, pick the second row, which is 0 minus 1 1, 0 minus 1 1. Now if you add them up, this is 2 3 4. Obviously this has to have 3 eigenvalues, but the non-zero eigenvalues are going to be lambda 1 is equal to 3, lambda 2 is equal to be 1, and then lambda 3 is equal to be 0. You can go home and check whether you get these 3 eigenvalues or not. So the non-zero eigenvalues are the same. The non-zero eigenvalues of A transpose A and AA transpose are the same. And so the singular values are, so this implies sigma 1 is equal to under root 3 and sigma 2 is equal to under root 1, which is simply equal to 1. Okay. So now I have sigma. So my sigma is actually 2 by 3. Sigma is 2 by 3. And what is this sigma 2 by 3? I have under root 3 here. I have 1 here. This is 2. And then I have 3. So this is 2 by 3. So I have 0 here. I have 0 here. This is my sigma, right? So these are the singular values. So sigma 1 over here. And this one over here. And what is the rank of this matrix? The rank of this matrix is, so let's check. So rank of A is simply, so these are the two non-zero rows. So the number of rows is, so number of independent rows is equal to 2. So this implies, which is equal to, so this implies rank is 2. Okay. So if the rank is 2, obviously we have these 2 values here, which are non-zeros. Okay, good. So what about, so let's find the eigenvectors of AA transpose. So what are the eigenvectors of AA transpose? So if lambda 1 equals 3, this implies AA transpose minus lambda I equals minus lambda 1 I equals, so 2 minus 3 is minus 1, minus 1, minus 1, minus 1. So this implies I can do minus row 1 plus row 2. If I do that, I'll get plus 1, plus 1, plus 1, so 0. 0 and 0, excuse me. And then if I multiply row 1 by minus 1, if I multiply row 1 by minus 1, this will be 1 and 1. So this implies U1 is going to be, so this one, so this is a pivot, so obviously the second one is a free variable, and I also normalize it over here. So this one becomes negative, and then becomes this one. What about U2? And if lambda 2 is equal to 1, this implies A transpose minus lambda 2I equals, so 2 minus 1 is 1, this is minus 1, this is minus 1, and 2 minus 1 is 1. So I simply do R1 plus R2. If I do that, I get 1 minus 1, 0, 0. So this is my pivot. So this implies U2 is going to be, this minus 1 goes on this side, becomes a plus 1 here, and this is the free variable. This is 1 over under root 2. And you can check U1 dot U2 is equal to 0, is equal to 0. So U1 and U2 are orthogonal, and they are already normalized. So what is V1 then? So since this is a fat matrix, so this is a fat matrix, so I am going to use A transpose. So this implies, so since A is fat, which implies M is less than N, right? So since M is less than N, then A transpose UI is equal to sigma I Vi for I is equal to 1, 2, up to R. And what is R here? R is equal to 2, so only 2. So what is A transpose? So A transpose is minus 1, 1, 0. So A transpose is minus 1, 1, 0, minus 1, 1, 0, and this is 0, minus 1, 1, 0, minus 1, 1. So this is A transpose. This is A transpose. If this is A transpose, U1 is 1 over under root 2 into minus 1, 1. This implies, and sigma 1 is under root 3. So this implies V1 from this equation, V1 from here, V1 is equal to 1 over sigma I. 1 over sigma I, this one is 1 over under root 6 into, so under root 6 is because under root 2 here, under root 3 here. And then I am picking, I am subtracting the first column from the second column. So I have 1 here, minus 1, minus 1, minus 2 here, and I have 1 here. And again, the length already is under root 6. This is already normalized. Okay. And what about U2? So A transpose U2 is going to be sigma 2 V2 from this equation, because R is equal to 2, and this implies V2 equals, so this is U2, sigma 2 is 1, this is 1, and this implies V2 is equal to 1 over root 2, and I simply add the two columns. So if I add two columns, I'll get minus 1, 0, and 1. And if you check these two columns, V1 dot V2, this is 0, right? So minus 1 plus 1, this is 0. And how do I get V3? So so the only thing left is V3, because V3, A transpose A is a 3 by 3 matrix, so it's a 3 by 3 matrix, so I have to have third. I'm not going to find it from here. I can find it from here too, but I'm going to actually use the null space. So I'm going to use the null space information, which says AVI. So A times V3 equals 0. Or maybe I write this. AVI is equal to 0 for I equals R plus 1 up to N. So this is 2 plus 1, which is equal to 3, N is equal to 3, so I only need 1. So V3 belongs to the null space of A. And what is A? Where A is simply minus 1, 1, minus 1, 0, 1, minus 1, 0, 1. And I can always do this. So I don't have to do this. I do plus here, minus here, plus here, minus here. So this is a pivot. This is a pivot. There is only one free variable, so this implies V3 equals, so these are two pivots, right? These are two pivots. So V3 is equal to, the third one is the free variable, so that is 1. This is 1, goes here, negative here, becomes a 1. This one goes here, negative here, becomes a 1. And this is 1 over root 3. And now check, are these, so check, so this is V3, so check V1 dot V3 is 0. Yes, this is 0. Why? Because this is simply sum of all these. So 1 plus 1, 2 minus 2 is 0. And V2 dot V3, is this 0? Yes. Minus 1 plus 0 plus 1 is 0. So both are all right. So, so this implies U is actually, what was U? U is minus 1 over under root 2, 1 over under root 2, and then I have 1 over root 2, and I have 1 over root 2. So this is U, and V is, what was V1? So V1 was 1 over under root 6. So 1 over root 6 minus 2 over root 6 and 1 over root 6. This is V1. V2 is minus 1 over root 2, 0, 1 over root 2, and finally I have 1 over root 3, 1 over root 3, 1 over root 3. And sigma I already told you, and sigma equals 2 by 3. So this was under root 3, 0, 0, 1, and this was 0, 0, right? And if you go home at your home, you actually calculate this one and see whether this one is equal to A or not. So check A equals U sigma V transpose, and you'll find that this is indeed the case over there. Okay. So use our eigenvectors. So use our eigenvectors of A transpose, or left singular vectors, or since they are on the left, or left singular vectors, and these are actually eigenvectors of A transpose A, or right singular vectors, because they are on the right singular vectors. So let's stop here. In the next chapter, in the next lecture, we are going to look at the applications of the singular value decomposition, and that should do for this, for chapter 6. We are not going to spend too much time on chapter 6. The important things are the singular value decomposition. How do you do singular value decomposition, and how do you, what are the applications of singular value decomposition? Probably the most important one is the least squares. Okay. So if you have any questions, we can discuss it on Mondays or Wednesdays. You can email me. Otherwise, I'll see you in the next, which is actually the last video recording of this course. Thank you.